Hello everyone, welcome to video number 4 of physics mechanics. This is the second video on forces, and in this video you're going to be learning about friction. And there are some topics from video number 3 that you'll need to recall for this video. They are Newton's 3 laws of motion, which were on inertia, F equals ma, and reaction forces, and the forces gravity and normal force. Gravity is 9.8 times m newtons on Earth, and normal force is the force that prevents an object from sinking into a surface. For an object that rests on a horizontal ground, it is equal to the force of gravity. But without further ado, let's get into friction. Friction is a force that acts upon an object when the object touches a surface and moves or tries to move. It always goes in the direction opposite of the direction that the object is moving or trying to move in. In this video, we're going to be exploring two types of friction, static and kinetic. Static friction acts on an object that is not moving and is trying to move. So let's suppose that a non-moving object is on the ground and an external force acts to the right on it. In that case, static friction will act to the left, and it will be equal to the magnitude of the external force. So since the two forces are equal, they balance out, and the non-moving object does not move. Now, if we increase the external force, the static friction will still be equal in magnitude to it, so the object still doesn't move. However, there is a maximum amount of static friction. So if the external force becomes greater than the maximum force of static friction, then the object will start moving. So an example of this in your own life is if you push a bookshelf or another heavy object, it likely will not move because the maximum amount of static friction is pretty high. However, if you apply enough force on it, then eventually it will be able to move. So kinetic friction acts on an object that is moving. So it goes in the opposite direction that the object is moving in. So here's an example. An object is moving right, and there are no external forces acting upon it. In that case, kinetic friction will go to the left. And even if there is an external force acting upon it, the kinetic friction will still go to the left because the object is moving right, and the magnitude of the kinetic friction is not changed. If the object moves left, then the kinetic friction will act to the right, even if the external force is also acting to the right. Is friction good or bad? The answer is both. However, we will see at the end of this free body diagram that it is more good than bad. So how do we draw the free body diagram for a person walking? Well, when you're walking, you're basically pushing backwards on the ground. And according to Newton's third law, if you push backwards on the ground, then the ground will push you forward. So that allows you to move forward. So therefore, the free body diagram might look something like this. Obviously, we have gravity and normal force, and then the back foot will be pushing backwards, so that allows friction to act forwards. And then if the front foot is not pushing backwards, then friction will likely act a little bit backwards. So this is what allows us to walk and control our speed and direction. If there wasn't friction, then we wouldn't have these forces, so we wouldn't be able to walk in the first place. Or if we were already moving, then we will just continue moving until we crash into something. So you might think that friction is bad because it requires us and cars to keep on applying energy to stay moving. However, just know that if there wasn't friction, we wouldn't be able to move in the first place, or if we were already moving, then we can't stop. Here is the formula for friction. F equals mu n, where F is the force of friction for kinetic friction, or maximum force of friction for static friction. So for kinetic friction, it's pretty straightforward. However, for static friction, remember that static friction is just equal to the external force, unless the external force is greater than the maximum force of static friction, in which case there is no longer any static friction. So keep in mind that max force of friction and force of friction aren't the same thing. If you're just asked to find the force of static friction, then you would still use this formula to determine if the external force is greater than the maximum force of static friction. However, the maximum force of static friction is not the answer. And then mu is the coefficient of static or kinetic friction. It's a number that's greater than 0, and it depends on the surfaces. If the surfaces are really smooth, such as ice, then it's a low number. If they're rough, such as concrete, then it's a high number. And I made surfaces plural because we care about both the object and what it's sliding against. We can't just care about one of those surfaces. And the coefficient of static friction is always going to be greater than the coefficient of kinetic friction. The reason has to do with intermolecular forces, which is not something that you'll need to know. And then N is the amount of normal force, which is usually determined by the amount of gravity. So here's an example problem. The coefficient of static friction is 0.7 and the coefficient of kinetic friction is 0.5. An object with a mass of 5 kilograms is sliding on the surface. What is the force of friction? So since this object is sliding, we know that it's moving. Therefore, we use the coefficient of kinetic friction. And then, therefore, the force of friction is just equal to 0.5 times the normal force, which is just 9.8 times the mass, 5. So the force of friction is equal to 24.5 newtons. Here's a practice problem. If you want to give it a try, then pause the video here. The solution will come in 3, 2, 1. For part A, we need to use static friction since the object is initially at rest. The maximum force of static friction is the coefficient of static friction, which is 0.6, times the normal force, which is 9.8 times 8. And this is equal to 47.04 newtons. And since the exerted force is 50 newtons, and that's greater than 47.04, the object moves. For part B, we need to use kinetic friction since the object is now moving, and that is equal to 0.4 times 9.8 times 8, which is 31.36 newtons. The net force is 50 minus 31.36. It's minus because the pushing force and the force of friction act in opposite directions. So this is equal to 18.64 newtons. So 18.64 is equal to the mass, which is 8 times A, and A is equal to 2.33 meters per second squared. Here's another practice problem. If you want to try it, pause the video here. The solution will come in 3, 2, 1. So let M1 represent the lighter object and M2 represent the heavier object. The kinetic friction acting on the lighter object is the coefficient of kinetic friction times the normal force, which is 9.8 times M1. And that's the force, and it's equal to M1 times A, and dividing both sides by M1 gives A is equal to the coefficient of kinetic friction times 9.8. And the kinetic friction on the heavier object is the coefficient of kinetic friction times 9.8 times M2. And that is equal to M2 times A. So A is equal to the coefficient of kinetic friction times 9.8. So therefore, the two objects have the same deceleration. Welcome to the first lab of this series. You're going to be learning how to determine the coefficient of static and kinetic friction. Now keep in mind that we're going to be using a simulation to do this lab, since doing it in real life would require tools that you likely don't have. If you want to try to do this lab by yourself, then in the description there's a link to a PhET simulation. Click on it, and also click on the link below it, which will take you to a data table, and you can make a copy of it so you can fill it out yourself. On the PhET simulation, click on acceleration and check values, masses, speed, and acceleration, and uncheck forces. So we're pretending that you have devices that can measure the mass, speed, and acceleration of any object, but you don't have a device that can measure the force of friction. You'll still know what the applied force is because it's displayed down here, and you can control it by yourself. It is recommended that you fill out the data table from top to bottom because each entry in the data table will guide you to the entries below it. And it's okay if your answers are not exact in this data table. You can approximate and or round to 2 decimal places. If at any point you're stuck, I would suggest watching the solution until I go over the part where you're stuck on, and then you can continue from there. But anyway, if you want to try to do this, then pause the video here. I will start explaining the solution in 3, 2, 1. So first we need to find the maximum force of static friction. So we just find what is the maximum applied force that we can give such that the box does not move. So let's just go 50, 100. And at 150, we see that the box starts moving because the acceleration is no longer 0. All right, so now let's just reset. So now we know that the maximum force of static friction is somewhere between 100 and 150. So now we just go one by one until we find the correct answer. This might take a few tries, so I'll just fast forward until I get to the right answer. All right, so at 126 newtons, we see that the box starts moving. So that means that the maximum force of static friction is somewhere between 125 and 126. We can just approximate and put 125. If you put any other value between 125 and 126, that's also acceptable. Now the mass of the object, we know that's 50 because that's displayed. And the normal force is just 9.8 times 50. You can use a calculator, or you might know off the top of your head that that is equal to 490. And remember that the maximum force of static friction is equal to the normal force times the coefficient of static friction. That means that the coefficient of static friction is equal to the maximum force of static friction divided by the normal force. So it is equal to 125 divided by 490, which is approximately 0.26. All right, so now we're done with static friction. And for kinetic friction, first of all, the pushing force, you can use any force you want as long as the box is moving, but we're just going to use 126. So the acceleration of the object was displayed as 0.64 meters per second squared. The mass of the object is 50. And the net force is the acceleration times the mass. So that is 32. And remember that the net force is equal to the pushing force minus the kinetic friction force. That means that the kinetic friction force is equal to the pushing force minus the net force. So 126 minus 32 gives 94. All right, the mass of the object is 50. And the normal force is equal to 50 times 9.8, which is 490. And then the coefficient of kinetic friction is equal to the kinetic friction force divided by the normal force. So that is 94 divided by 490, which is approximately 0.19. All right, so these are all of the answers. And now we are finished with the lab. The last topic for this video is ramps, also known as inclined planes. Ramps are generally used to get an object to a particular height. The steepness of a ramp is very important to consider because if it's too steep, then the objects might slide down by themselves. And if it's not steep enough, then the ramp would have to be longer in order to get objects to the same height. You're going to be learning how to determine the proper steepness of a ramp. If you put an object on a tilted surface, what will happen? Well, let's first draw the free body diagram for it. We have gravity, normal force, and friction acting upon it. Gravity always acts downwards. Normal force always acts perpendicular to the surface. Friction always acts parallel to the surface. In this case, gravity is trying to cause the object to slide downwards, and friction counters that. We're not used to a free body diagram like this because for many of the free body diagrams that we've seen, many of the forces lie on the axes. And in this case, we have two forces that do not lie on the axes. So how can we fix that? The answer is that we can rotate the axes such that friction lies on the x-axis and normal force lies on the y-axis. Now we only have one force, gravity, that does not lie on either axis, so we can just break it down into its components. So notice that theta, the angle of inclination, is also the angle between gravity and the y-axis. So the new x component of gravity is 9.8 times m, which is just the force of gravity, times sine theta, and the new y component of gravity is 9.8 times m times cosine theta. Now this might seem backwards because you're used to seeing cosine for the x-axis and sine for the y-axis. So why is this backwards? The answer is because theta is the angle between gravity and the y-axis. In all previous examples that you've seen, it was the angle between the vector and the x-axis. So this is why we switched them around in this case. So after breaking down gravity into its components, your free body diagram might look something like this. If normal force was greater than the y component of gravity, then the object would rise into the air. If it was less than the y component of gravity, then the object would sink into the surface. So it can't be less than or greater than the y component of gravity. Therefore, normal force has to be equal to the y component of gravity. And if you know the coefficient of friction and the normal force, you can calculate the force of friction. So you don't use the x component of gravity to calculate friction, you just use the normal force. So here's an example problem. A ramp has an inclination of 60 degrees. An object is moving and the coefficient of kinetic friction is 0.5. The mass of the object is 10 kilograms. What is the force of friction? So we first need to determine the y component of gravity. That is 9.8 times 10, which is the mass of the object, times cosine of 60 degrees, which was the angle of inclination. And this is equal to 49 newtons. And the normal force is also equal to that. So the force of friction is the coefficient of kinetic friction, 0.5 times 49, which is 24.5 newtons. Here's another example problem. A ramp has an inclination of 10 degrees. An object initially at rest has a mass of 10 kilograms. If the coefficient of static friction is 0.1, does the object slide down the ramp? Well, we need to determine first the y component of gravity, which is 9.8 times 10 times cosine of 10 degrees, which is 96.51 newtons. And the normal force is also equal to that. The maximum force of static friction is equal to the coefficient of static friction, 0.1 times that. So it's equal to 9.65 newtons. The x component of gravity, because that is the force that is trying to cause the object to move down the ramp, is equal to 9.8 times 10 times sine of 10 degrees, which is 17.02 newtons. And since 17.02 is greater than 9.65, the force that is trying to cause the object to move down the ramp is greater than the force that is trying to prevent it from moving down the ramp. So therefore, the object does slide down the ramp. So here's a practice problem, and it might seem like there's missing information since you don't know the mass of the object, but remember that we previously did a problem where we saw that the deceleration of two objects with different mass is the same. So try to see if you can use a variable for the mass and later cancel it out. But anyway, if you want to give it a try, pause the video here. The solution will come in 3, 2, 1. The y component of gravity is 9.8 times m times cosine of 45 degrees, and that's equal to 6.93 times m newtons, and that's also what the normal force is equal to. The force of friction is equal to 0.6 times that, which is 4.16 times m newtons, and the x component of gravity is 9.8 times m times sine of 45 degrees, which is 6.93 times m newtons. And since the object is sliding upwards, that means the force of friction is acting in the same direction as the x component of gravity. So therefore, the x component of the net force is obtained by adding together the x component of gravity and force of friction. So you get 11.09 times m newtons, and that is equal to m times a, and canceling out m, you get a is equal to 11.09 meters per second squared. So that is the deceleration. And deceleration is a weird term, and scientists generally don't like to use it. But when you see a problem that asks for it, then generally you should just calculate the acceleration and then report the absolute value of the answer. So here's another practice problem. If you want to give it a try, pause the video here. The solution will come in 3, 2, 1. So we want to find the angle such that the x component of gravity is equal to the maximum force of static friction that prevents the object from moving. So we have 9.8 times 5 times sine of theta is equal to the coefficient of static friction, 0.7 times 9.8 times 5 times cosine theta, and 9.8 times 5 times cosine of theta is just a normal force. So isolating theta and dividing both sides by 9.8 times 5, you get tangent of theta is equal to 0.7. So theta is equal to arctan of 0.7, which is approximately 34.99 degrees. So a quick recap of this video. You learned about static and kinetic friction. The friction formula is F equals mu n. We did a lab on determining the coefficients of friction. Basically, you first find the force or max force of friction, and then knowing that along with the normal force allows you to solve for the coefficients of friction. And then the final topic was ramps. Basically, you tilt the axes such that normal force and friction fall on the axes, and then you break gravity down into its components, and then you solve for normal force and then friction. Thanks for watching. I'll see you in video number 5.